So what is a logarithm? In simple terms, logarithms are the inverse of the exponent. The formal definition of a logarithm is that if log base a of b is equal to x, then a to the power of x is equal to b. So what does this really mean? Suppose we have something like log base 2 of 8. What this is really saying is 2 raised to what power is equal to 8. We know that 2 to the power of 3 is equal to 8. So log base 2 of 8 is equal to 3, according to the definition. Log is just short for the word logarithm, so when we say log base 2 of 8, we really mean the logarithm base 2 of 8. The number in the subscript is always the base, so in this case, the base is 2. So let's say we have something like log base 3 of 81, and we want to find what that equals to. We can set log base 3 of 81 to equal x, and this means 3 to the power of x is equal to 81, going by the definition. Well, we know that 3 to the power of 4 is equal to 81, so this means x is equal to 4. Since x is set to be equal to log base 3 of 81, this implies the value of log base 3 of 81 is equal to 4. This makes sense because finding the value of log base 3 of 81 is basically trying to find 3 to what power is equal to 81, and the answer is 4, since 3 to the power of 4 is equal to 81. So it's also possible to find the values of these logarithms without using the formal definition, and it's probably easier to start this way. So let's say we have log based 5 of 125. Well, this is just asking the question, 5 to what power is equal to 125? We know that 5 to the power of 3 is equal to 125. So this means log based 5 of 125 is just equal to 3. So let's go over a few more examples to get a better idea of how logarithms work. If we have log base 2 of 64, we are trying to find 2 to what power is equal to 64. We know 2 to the power of 6 is equal to 64, so that means log base 2 of 64 is equal to 6. By the way, the number in the subscript is called the base, and the number at the top is called the argument. So in log base 2 of 64, the argument is 64. For the second example, log base 7 of 49, we need to ask the question, 7 raised to what power equals 49? So we know that 7 squared is equal to 49. So 7 raised to the power of 2 is equal to 49. So this means log base 7 of 49 is just equal to 2. For log base 3 of 27, we need to determine 3 raised to what power is equal to 27. Well, 3 cubed is equal to 27. So this means log base 3 of 27 is equal to 3. So the same thing for log base 4 of 256. We need to ask 4 to what power is equal to 256. Well, 256 is just 4 to the power 4. So 4 to the power 4 is equal to 256. So this means log based 4 of 256 is equal to 4. Sometimes we will encounter logarithms with negative or fractional values. So in the first example, log base 2 of square root of 2, we need to ask the question, 2 raised to what power is equal to the square root of 2? So the square root of 2 is actually just equal to 2 to the power of 1/2. So this means 2 raised to the power of 1/2 is equal to the square root of 2. Therefore, log base 2 of the square root of 2 is just equal to 1/2. So for the next example, log base 3 of 3 square root of 3, we need to determine what power we need to raise 3 to in order to result in 3 square root of 3. So 3 square root of 3 is actually equal to 3 to the power of 1 times 3 to the power of 1/2, because 3 is just equal to 3 to the power of 1, and the square root of 3 is equal to 3 to the power of 1/2. So using the exponent laws, we can combine this into a single expression, 3 to the power of 1 plus 1/2, and that just simplifies to 3 to the power of 3 over 2. So this means 3 square root of 3 is equal to 3 to the power of 3 over 2. So we need to raise 3 to the power of 3 over 2 in order to result in 3 square root of 3. So this means log base 3 of 3 squared root of 3 is equal to 3 over 2. So for the next example, log base 2 of 1/2, we need to rewrite 1/2 as 1 over 2 to the power of 1, and by the exponent laws, we know that 1 over 2 to the power of 1 is just equal to 2 to the power of negative 1. So this means we need to raise 2 to the power of negative 1 to result in 1/2. So log base 2 of 1/2 is just equal to negative 1. And this is an example of a logarithm with a negative value. So to evaluate log base 5 of 1 over 25, we first need to rewrite 1 over 25 as 1 over 5 squared, since 25 is just equal to 5 squared. And we can rewrite this as 5 to the power of negative 2 with exponent laws. So we need to raise 5 to the power of negative 2 in order to result in 1 over 25. So log base 5 of 1 over 25 is equal to negative 2. So another thing to consider is logarithms with fractional bases. So suppose we have something like logarithm based 1/2 of 1/8. Well, we can rewrite 1 over 8 as 1 to the power of 3 over 2 to the power of 3, since 8 is equal to 2 cubed, and 1 is technically equal to 1 to the power of 3. So we can rewrite the entire fraction as 1/2 to the power of 3. So this means we need to raise 1/2 to the power of 3 in order to result in 1/8. So this means log based 1/2 of 1/8 is equal to 3. So what about something like log base 1/5 of 25? Well, we can think of 25 as 25 over 1, and then we can divide both the numerator and denominator by 25. So we end up with 1 over 25. Well, the 1 over 25 in the denominator can be thought of as 1/5 squared. So using exponent laws, we can rewrite this as 1/5 to the power of negative 2. So 25 is just equal to 1/5 to the power of negative 2. So we need to raise 1/5 to the power of negative 2 in order to result in 25. So log base 1/5 of 25 is just equal to negative 2. So there's another thing we need to consider, and that's the common logarithm. A common logarithm is a log of base 10, and we usually write this without the base. So when we say log of b, what we really mean is log base 10 of b, and we might put brackets around the argument b, but we sometimes just omit the brackets, but it basically means the same thing. So if we have the common logarithm, log of 10, this is the same as log base 10 of 10, and we know that 10 to the power of 1 is equal to 10. So we need to raise 10 to the power of 1 to result in 10. So this means log base 10 of 10 is just equal to 1. And since that's just equal to log of 10, we know that log of 10 is equal to 1. So we need to apply the same principle for the second example, log of 100. So we need to determine 10 raised to what power is equal to 100. So we know that 10 to the power of 2 is equal to 100. So this means log of 100 is just equal to 2. And the same thing for the third example, log of 1 over 100. What power do we need to raise 10 to in order to result in 1 over 100? Well, we know that 10 to the power of negative 2 is equal to 1 over 100. So this means log of 1 over 100 is just equal to negative 2. So one thing we need to be careful about is when a logarithm is even defined. So if we're only considering real numbers, then a logarithm is only defined if the base is greater than 0 and not equal to 1. So this means the base has to be positive, and you can't have logarithm with a base of 1. And the argument, which is the top part of the logarithm, also has to be positive. So if we have log base a of b, this means a has to be greater than 0, and also a is not equal to 1, and b also has to be greater than 0, and all of these conditions have to hold in order for the logarithm to be defined in the real numbers. So here's a little exercise to illustrate this. Suppose we have log base x plus 2 of negative 2x plus 3, and we want to find the range of values of x for which this logarithm is defined. In order for this logarithm to be defined, we need the base, x plus 2, to be greater than 0, and also not equal to 1. And we also need the argument, which is the top part of the logarithm, negative 2x plus 3, to be greater than 0. So we need x plus 2 to be greater than 0. And this just implies x is greater than negative 2. And we also want the base x plus 2 to not equal 1. So x plus 2 is not equal to 1, and that simplifies to x is not equal to negative 1. So the other condition is that the argument, negative 2x plus 3, has to be greater than 0. So if we subtract 3 from both sides of the inequality, we get negative 2x is greater than negative 3. And now we need to divide by 2 on both sides of the inequality. So we get x is less than 3 over 2. And we need to flip the sign of the inequality since we were dividing by a negative number. So if we combine these inequalities together, we get negative 2 is less than x, which is less than 3 over 2, and x is not equal to negative 1. So basically, x has to be between negative 2 and 3 over 2, and also x is not equal to negative 1. And these are the range of values that x must take in order for this logarithm to be defined. In the next video, I will be going over the basic properties of logarithms and the problem types that can be solved using these properties.